Okay, believe it or not, here we are, the last lecture in chapter 6, a very dense chapter, lots of important things happening in this chapter based on all of the prior knowledge from chapters 1 through 5 now. We're ready to do some real chemistry, so let's go ahead and finish up this chapter. Up until now, we've been focusing mainly on the chemistry, the starting materials and the products that we make. But of course, there's energy that accompanies most chemical changes, heat or light or some other form of chemical potential being converted into another type of energy. So that's our focus now in this last chapter 6 lecture, is to take a look at the energy changes in chemical reactions. Before we focus on that energy, let's talk about the conditions required for a chemical reaction to occur. We just sort of take it for granted that we write these chemical equations and therefore, well, the molecules have to do what we say, and that's certainly not true. First of all, we need to satisfy the collision requirement. The reactants must collide. There has to be physical contact. Chemistry is not a long-range distance sort of reaction. It involves atoms, molecules, formula units actually coming into contact with other reactants and changing their makeup at the fundamental level. The second requirement is that they have to collide in the right way. So just because two molecules collide doesn't mean there's going to be a reaction. If there's a reactive end of the molecule and an unreactive end of the molecule, and you have molecules colliding in such a way that the non-reactive ends hit, then just because they collided doesn't mean there'll be a reaction. They have to collide first, and then second, they have to fulfill that orientation requirement. They have to be aligned properly to break the current bonds in the reactants and form those new bonds to make those new products. And finally, not only do they have to hit each other, not only do they have to hit each other in the right way, but they also have to hit each other with sufficient energy. You have to have enough energy in that collision to break those current bonds and form the new bonds. It always requires energy to break a bond. If we have our starting material, it's stable. That's why we can manipulate it. And in order to break down that stable starting material, we've got to hit it with enough energy to break the existing bonds and hopefully have even more stable products, but at least have that sufficient energy to begin the reaction. So if we don't satisfy these three requirements, there won't be a reaction, and oftentimes collisions don't lead to successful reactions. But because we're dealing with very small, very numerous molecules moving very quickly, it seems to go very fast to us at the macro scale, even though there's a lot of unsuccessful collisions happening at the atomic scale. The name we give to that initial input of energy is the activation energy, and that's the amount of energy required to break those existing bonds between the atoms of the reactants and allow those reactants to react to form the products. So if we have a collision with less energy than the activation barrier, then the molecules just bounce apart without reacting. If we get some successful collisions and we generate energy as a result of the reaction, which is often the case, the products are more stable, lower in energy than the reactants, then that energy can provide additional activation energy for other collisions, and it can cause the reaction to go very fast. If you have a very favorable change from a relatively less stable molecule to a relatively more stable molecule, then it can go very fast because it's providing energy for additional collisions. But most of those collisions that occur in the reactants are unsuccessful. It's just because these things are so small and moving so fast that even with all those unsuccessful collisions, either because they were insufficient energy or the improper orientation, we eventually get lots of successful collisions and we cause the reaction to go forward. So despite the fact that there's a lot of failures, the successes when they occur help give rise to enough energy for neighboring molecules to make their successful collisions as well. Now, that's not always the case that we end with lower energy products and we release energy as heat that allows for additional molecules of reactant to overcome the activation barrier. That's the exothermic reaction case that we see on the left. But we also have the endothermic reaction case where we actually put in a lot of energy into the reactants and the activation barrier, as you can see, those activation energies are a little extra input compared to the final reactant or product state, but in the endothermic case, the products are actually higher in energy than the reactants. So it happens sometimes as well that we can have reactions that absorb heat and end up with higher energy products. And if you've ever used a chemical cold pack, particularly at athletic events, if there's an injury, typically a cold pack is used, and that's an example of an endothermic reaction. It gets cold fast because the dissolution of that solid into water typically is an endothermic process. We think typically about exothermic reactions that give off heat, like burning wood or other hydrocarbons to get heat and light for fuel in fireplaces or in our automobiles. So the exothermic reaction tends to be the one we focus on, but endothermic reactions do happen and they are important, and that example of chemical cold packs is hopefully a real world example that you've experienced, that you understand that, yeah, there are reactions that absorb energy instead of just releasing it. Now, instead of just talking about reactions as either giving off heat or taking on heat, we can actually do some math here. We can talk about what's called the heat of reaction, and that's the actual amount of heat absorbed or released during a reaction. So it's the difference, the mathematical difference between the energy of breaking the bonds in the reactants, and that always requires energy, and then the energy we release when we form bonds in the product. So bond breaking always requires energy, bond forming always releases energy, and we're just looking to compare, did we release more energy in making those new bonds than we had to put into breaking the old bonds, or was it the reverse? And that's going to tell us if we have an endothermic or an exothermic case. We use the symbol delta H, that's the capital Greek letter delta, and delta H is equal to the heat of the products, the enthalpy, if you want to get a really technical term, of the products, minus the sum of the heat of all the reactants. And so we're looking at really all those bonds and the bond breaking and bond making, and we see, do we end up with something that is overall a release of energy from reactants to products, or an absorption of energy from reaction to products? So if we go up in energy from product to reactant, like our picture shows, well, then that delta H is going to be a positive value. There'll be more enthalpy in the products than in the reactants. If we had the reverse case, where the products are a lower energy state and the reactants are a higher energy state, and we give off that excess energy as heat, we would have a negative delta H. And so here we see that fulfilled. In an exothermic reaction, the energy of the reactants is greater than that of the products, so heat is released along with converting those reactants into products. And because we're comparing the products to the reactants, our deltas in chemistry are always reactants being taken last, products being considered first. So when we take the energy of those products, which is a lower number, and we subtract the energy of those reactants, which in an exothermic reaction is a higher number, we end up with a negative sign. And in this case, for this specific reaction of solid carbon, charcoal with oxygen gas, making CO2, well, that releases a lot of energy, 394 kilojoules per mole of carbon reacted. So that's delta H of negative 394 kilojoules. That negative indicates the heat is released. Okay, let's consider now the endothermic case. Okay, so conversely, in an endothermic reaction, we have the energy of the reactants is lower than the energy of the products. So when we take our delta H, which is products minus reactants, we have the higher value for the energy of the products minus the lower value for the energy of the reactants, and we end up with a positive value. So here we see an example where nitrogen gas and oxygen gas react to form nitric oxide, or nitrogen monoxide if we want to use our official naming rules we learned earlier in the course. And in this case, that delta H says that for every mole of nitrogen that reacts with every mole of oxygen, it requires 180 kilojoules of heat energy. And so this is one reason why nitrogen gas is relatively inert. It takes a lot of energy to get it to react, and that may not sound like a lot, the 180 kilojoules, but again, in order to get that locally in the area where the nitrogen and the oxygen are colliding, we need something like a bolt of lightning to allow for that reaction. Just normal conditions of temperature and pressure, nitrogen and oxygen will not react because they don't have the energy to overcome that activation barrier. All right, so to summarize just qualitatively without putting numbers in here, an endothermic reaction has energy absorbed as heat when you go from reactants to products. So the heat is put in the reactant side, and the delta H has a positive sign because the enthalpy of the products is greater than the enthalpy of the reactants, which is how we always subtract things in a delta. We always do final state minus initial state, or in the case of chemistry, products minus reactants. For the exothermic example, now the heat is released, and the heat is released on the product side as you're making those products. You would indicate that there's also heat. Heat's not a reactant or a product, but we show it on a reactant side in an endothermic reaction, and we show it on a product side in an exothermic reaction. And in the case of an exothermic reaction, because the products are a lower energy, a smaller value subtracted from a higher value for the energy of the reactants, we get a negative sign for delta H. All right, so we've hit on a lot of important things in a chapter that's already been very conceptually dense. So let's pause here for a learning check and just take a step back from this idea of energy changes in chemical reactions and see how you do if you can just look at these three examples and identify them as exothermic or endothermic. And of course, you're going to be looking for either energy as heat or just the energy value in kilojoules. Depending on the side on which it occurs, that'll help you to identify as exothermic or endothermic. Take a moment here and pause the video, start us back up once you've made your determination, and we'll see how you did. Okay, so for our first reaction equation, we have heat on the product side, right? The plus 22 kilojoules, the energy at least is released. So heat is the typical way it's released, and it's on the product side. So the reaction is therefore exothermic, giving off heat. Lower energy products, higher energy reactants. For the second equation there, now we have that plus 133 kilojoules on the left-hand side, the reactant side. So that indicates it needs to be present to allow the reaction to progress. And if heat's treated like a reactant, then the reaction is endothermic. It requires heat to be put in, and it results in higher energy products from a lower energy reactant. Finally, in our third equation, we have just the word heat, no specific value, but again, because it's present on the product side, just like the first case where we did have a numerical value in kilojoules, wherever heat, whether just as heat or as a numerical value in kilojoules or some other energy unit like calories, if it's on the product side, then therefore the reactant is exothermic, whereas in that middle case on the reactant side, the reaction is therefore endothermic. Okay, as we've done for so many calculations so far in the course, let's look at a guide on how we're going to use these heat of reaction values to end up with actual numerical results. So first we need to state the given and needed quantities. Then we need to write our plan using heat of reaction and molar masses. If we're given it in grams, for instance, typically our enthalpies are per mole, so we'll need to do a mole conversion using molar mass. Next step, we'll write the conversion factors, including the heat of reaction, which we've ignored up until this part of chapter 6. And then finally, we can set up the problem to calculate the heat either absorbed or released. Again, the sign will tell us whether the reaction releases heat or absorbs heats, depending on the plus or minus, and then also the numerical part will tell us how much heat is absorbed or released. All right, so let's work this example together for calculating the heat of a reaction. If 15.0 grams of nitrogen monoxide are produced according to the following reaction, how many kilojoules were absorbed? So we have 1 mole of nitrogen gas plus 1 mole of oxygen gas yields 2 moles of nitrogen monoxide gas, and that is an endothermic reaction. I know that because the delta H is positive, and it requires 180 kilojoules per mole of N2 and mole of O2 reacted, and that 180 kilojoules is per 2 moles of NO that gets produced. Okay, so let's go ahead and analyze this thing. Step 1, state our given and needed quantities. So we're given 15.0 grams of NO. Our delta H is a plus 180 kilojoules. We don't have to show the plus, we understand it to be there, but we definitely want to show a minus if we end up with one of those scenarios. And finally, we need to know the kilojoules of heat actually not produced, but absorbed in this case. And we have the balanced chemical equation to help us with that. Moving on to step 2, now we'll write our plan using heat of reaction and any molar mass data needed. So we start in grams of nitrogen monoxide. Obviously, we'll need its molar mass to get into moles of nitrogen monoxide, which is what the reaction actually talks about. And then finally, we'll use our value of the 180 kilojoules per 2 moles of NO produced to find the kilojoules of heat absorbed in this reaction. Okay, here we are in step 3. We're ready for those conversion factors, including that heat of reaction. And so we know from the periodic table, 1 mole of nitrogen has a mass of 14.0 grams. 1 mole of oxygen has a mass of 16.0 grams. Therefore, when we add 14.0 grams from the mole of nitrogen plus 16.0 grams from the mole of oxygen in our mole of NO, we end up with 30.0 grams. So that's the molar mass. And since we're starting with the 15.0 grams of NO, we're probably going to want the 1 mole NO over 30.0 gram form of that nitrogen monoxide molar mass. The other thing we need to know is that 2 moles of NO equals a plus 180 kilojoules, and obviously we could have that conversion factor in either form that you see there, but what will dictate which form we use is the setup, the dimensional analysis setup for our reaction in step 4. And here we are on to step 4. We've set up the problem to calculate the heat. So we start with that 15.0 grams of NO. We convert through using the molar mass to find moles of NO. And then we have the 180 kilojoules per 2 moles of NO, which allows the mole of NO to cancel and give us a value of 45.0 kilojoules of heat absorbed in that reaction. Okay, so the dimensional analysis setup was set up correctly. We end up with the value, again, 3 sig figs in our starting mass of the NO, and so 3 sig figs in our final value here. And if you want to be extra careful, you could put a plus sign to be clear that this is 45.0 kilojoules absorbed in the course of the reaction. All right, so now that we've had some practice together, why don't you go ahead and try one on your own here with a learning check. In this example, we have the question, how many grams of O2 reacted if 306 kilojoules were released in the following reaction? And we see 1 mole of methane gas plus 2 moles of oxygen gas yields 1 mole of carbon dioxide gas plus 2 moles of liquid water plus 213 kilojoules of energy. So we have more than 213 kilojoules, a total of 306 kilojoules released in this learning check. So we know we should have more than 2 moles of oxygen if the 2 moles of oxygen would only produce the 213 kilojoules. But you need ultimately grams of oxygen. So hopefully you can follow our procedure to find that. Pause the video now. It'll take a few moments to find that, I'm sure, and then start us back up once you've solved this thing and selected your multiple choice answer. Okay, so walking through the steps, hopefully you did all these steps on your own, but just to be safe, we'll do them together here. Step 1, state the given and needed quantities, and when we analyze this problem, we see that 306 kilojoules are released in this particular example. The delta H of the reaction is a minus 213 kilojoules per mole of CH4 and per 2 moles of O2. We need ultimately the grams of O2 reacted to give us that 306 kilojoules of heat released, and we have our balanced chemical equation at our disposal. All right, so moving on to step 2, we'll write our plan using heat of reaction and molar mass. And obviously, since we're ultimately looking for a mass value of oxygen, we'll need to use at least the molar mass of O2, diatomic oxygen, one of our 7 diatomic molecules. So we'll start in the kilojoules of heat released. We'll use the heat of reaction to find the moles of O2, and then finally we'll use that molar mass value to get moles of O2 converted into grams of O2. And by looking at that reaction, we find that 2 moles of O2 yields 213 kilojoules of heat as it reacts. And therefore, we can have that conversion factor in either form with the moles up top or with the moles down below. We also know that 1 mole of O2 equals 32.0 grams of O2, right? 1 mole of O would be 16.0 grams. And so since we have O2, we now have twice that amount, and we can use that relationship as a conversion factor in either form as well. Finally, moving on to step 4, set up the problem to calculate the mass of O2. So we start with that 306 kilojoules that we're given. We multiply through by the form with the kilojoules in the denominator so that we are now converted into moles of O2. And then finally, we multiply through by the molar mass of O2 to get grams of O2. And the correct answer, 91.9 grams of O2, was answer choice A. Hopefully that's what you found. Hopefully this is very comfortable territory already for you. But if that's not the case, please do try some additional practice problems where you're looking at reaction energies and solving problems like those that we've worked together and the learning checks that you've done on your own. If it's still not making sense, you're not getting the concept, then please, of course, reach out to me and ask for some help, and I'll do my best to help you. Otherwise, we will meet again for Chapter 7.